Welcome to Godwills.
Hey everyone, this is Satish and welcome back to Godwills Talent Hub. Today, we are diving into something absolutely fundamental to mathematics. Number systems. From counting your fingers as a kid to calculating rocket trajectories, numbers are everywhere. But did you know there are actually different types of numbers and each one has its own superpowers? By the end of this video, you will understand exactly how natural numbers, whole numbers, integers, rational numbers, irrational numbers, real numbers, and even complex numbers all fit together. So buckle up, hit that like button, and let's jump in. Alright, let's start with the basics. What are numbers? Numbers are the language of mathematics. We use them for four main things. First, for counting. How many apples do you have? How many subscribers did we gain today? That's counting. Second, measuring. How tall are you? How far is your school? How much does that cake weigh? Numbers help us measure everything. And the third one, calculating. Adding your grocery bill, subtracting the expenses, multiplying, dividing pizza slices. That's all calculation. And fourth, ordering. Who came first in the race? What's the biggest mountain? Numbers help us arrange and compare things. Pretty cool, right? Now let's explore the different types of numbers. Let's kick things off with the simplest numbers of all, natural numbers. These are the numbers you learned when you were a toddler. 1, 2, 3, 4, 5, and they go on forever to infinity. We represent them with this fancy symbol, capital N. That's double-lined N. The formula is simple. Natural numbers, the capital N, is a set of numbers 1, 2, 3, 4, 5 and goes on till infinity. Here is what makes natural numbers special. They start from 1 and go to infinity. They are used for counting objects. They are all positive integers, no zero, no negatives, no fractions, just pure, simple counting numbers. Think of them as the OG numbers, the originals that started it all. Let's see natural numbers in action. Look at these beauties. 1, 5, 10, 100, 999, 1 million. All these are natural numbers. But where do we use them in real life? Counting apples? 1 apple, 2 apples, 3 apples, 4, 5. You get the idea? Page numbers in a book? Page 1, page 2, page 3. Every book uses natural numbers. House numbers? Your address? 10, 11, 12, 345. All are natural numbers. Age? How old are you? 1 year old, 5 years old, 25 years old. That's natural numbers at work. See, you have been using these your entire life without even thinking about it. Alright, now let's level up. Meet the whole numbers. Whole numbers are basically natural numbers cool cousin who includes 0 in the gang. And it is represented with the capital letter W, and it is a set which comprises 0, 1, 2, 3, 4, 5 till infinite. See that 0 at the beginning? That's the only difference. Let me break it down for you. Natural numbers, they start from 1, 1, 2, 3, 4. Whole numbers start from 0. That is 0, 1, 2, 3 and so on till it goes till the infinity. That's it. Just one number makes the difference. Pretty simple, right? But why is 0 so important? Because sometimes you need to represent nothing. So how do we represent nothing? Like 0 apples, $0, 0 points, right? You need a number for that too. But things are getting interesting. Welcome to integers, represented by this capital letter Z, and that's the double line Z for you. Integers include -3, -2, -1, 0, 1, 2, 3, and so on. Look at that. Integers go in both directions. Here is what we have got. Positive integers 1, 2, 3, 4 like all the natural numbers, negative integers, -1, -2, -3, -4, and so on. 0, sitting right in the middle, neither positive nor negative. And just like before, no fractions, no decimals, just whole numbers. But now we can go negative as well. Let's see integers in the real world. Check out these examples. -100, -5, 0, 7, 50. All these are integers. Where do we use negative numbers? Temperature. -5 degrees centigrade, 0 degrees centigrade. Bank balance, -500 rupees or plus 1000 rupees. Elevation, -50 meters below the sea level or 0 meters, which is right the sea level, and 100 meters above the sea level. Building floors, -2, a basement level, 0, ground floor, 5, fifth floor up. Negative numbers help us represent things below 0, less than 0, or going in the opposite direction. Now we are entering the world of fractions and decimals. It is represented with the capital letter Q, and they are said to be rational numbers. On the screen, when you look at the formula, Q is equals to P by Q, PQ belongs to Z, and Q not equals to 0. Wow, what does that mean? Let me break it down for you. A rational number is any number that can be written as a fraction. That's P divided by Q, where P and Q are both integers and Q cannot be 0 because you can't divide by 0. That's a big no in math. Rational numbers include fractions like 1 by 2, 1 by 4, 1 by 3, 2 by 3, and so on. Terminating decimals like 0.5, 0.75, 2.8. Repeating decimals like 0.3333. It goes on forever. The key word is rational because they can be expressed as a ratio. Right, let's see some examples. Fractions, half, 1 by 4, 2 by 3, -3 by 4. Decimals, 0.5, 0.75, -2.5, 3.0. Let's look into the real life uses. Sharing pizza, cutting it into half or 1 by 4 or 1 by 8 slices. Money, 2 rupees and 50 paise, $10.75. Measurements, 2.5 kilograms, 1.75 liters of oil. Super useful in cooking and science. Irrational numbers. Hold on to your hats, folks. Now we meet the rebels of the number world. Irrational numbers. These are numbers that cannot be written as fractions, no matter how hard you try. Famous examples: pi, √2, Euler's number, and the golden ratio. Here is what makes them irrational. They cannot be expressed as P by Q. Their decimals are non-terminating and as well as non-repeating. Let's look at pi. 3.141592653, and it goes on forever with no repeating pattern. And look at √2, 1.414213, something like forever and ever. And when you look at the Euler's number, 2.782818, another infinite, non-repeating decimal. These numbers are wild, unpredictable, and absolutely essential in mathematics. Let's meet the famous 4 irrational numbers. Pi, the ratio of a circle's circumference to its diameter, used in every circular calculation. √2, the square root of 2, and the ancient Greeks freaked out when they have discovered this. Euler's number, super important in calculus and exponential growth. The golden ratio, found in nature, art, architecture, it's the perfect proportion. These numbers might seem random, but they are everywhere in nature and mathematics. Alright, now let's bring everyone together. Welcome to real numbers. It is represented with the capital letter R, and real numbers include both the rational as well as irrational numbers. Here is the cool part. Every real number can be placed somewhere on the number line. Examples of real numbers: -5, 0, 1 by 3, pi, √2, 7.5, -2.8. All these are real numbers. Bottom line, if you can measure it, count it, or plot it on a number line, it's a real number. Everything we deal with in everyday life, real numbers, science, engineering, finance, cooking, all real numbers. Now we are entering the twilight zone of mathematics. Meet the complex numbers. It is represented with the letter capital C. When you look at the formula, it says A plus BI. A, B belongs to R. I square is equals to -1. So complex numbers have two parts. A, the real part. BI, the imaginary part. And I is equals to root of -1, the imaginary unit. Wait, what? The square root of -1? In regular math, you can't take the square root of a negative number. But mathematicians said, you know what? Let's imagine we can. And boom, imaginary numbers were born. Examples: 3 plus 4i, -2 plus 5i, 7 minus 3i. These might seem weird, but they are crucial in engineering, physics, and quantum mechanics. Let's see complex numbers in action. As you look at the screen, there are examples. Why do we need complex numbers? To solve equations like x squared plus 1. In regular math, there is no solution. But with complex numbers, x is equals to plus or minus I. The problem solved. And about the real world uses, electrical engineering, it is used to analyze the AC circuits, quantum physics, describing particle behavior, signal processing, audio, video, and communication systems. Even though you can't see complex numbers on a regular number line, they are absolutely essential for modern technology. Alright, let's see how all these numbers relate to each other. Think of it like a family tree or Russian nesting dolls. Each one contains the previous one. Natural numbers, all the counting numbers that we use. Whole numbers, it includes 0 with the natural numbers. Integers, it includes negative numbers with the whole numbers. Rational numbers, it includes the integers. Along with that, adds on fractions and decimals. Real numbers, it includes the rational numbers and irrational numbers like pi, √2 or Euler's number. Complex numbers, it includes the real numbers and the imaginary numbers as well. So each level includes everything before it. Natural numbers are inside whole numbers, which are inside integers, and so on. That's the complete hierarchy. Let's do a quick comparison so you can remember the differences. Natural numbers start from 1, 2, 3. There is no 0, no negatives, no fractions, and used for counting objects. Integers include -2, -1, 0, 1, 2, and goes on. There is a 0 in it. There are negatives in it, but no fractions. And it is used for temperature and bank balance. Rational numbers include the fractional numbers as well as the decimal numbers. 0 is included, negatives are included, and it is especially used for money and measurements. Real numbers, it includes pi, √2, Euler's number, and all of the above. Everything above, like whatever you see in the list, everything is included in the real numbers. Even irrationals are included. It is specially used for science, engineering, in fact, for everything. Each type solves different problems. That's why we need all of them. Now, let's talk about some cool properties these numbers have. Closure property. If you add two natural numbers, you get another natural number. Example, 2 and 3. When added together, we get 5. So 2, 3 and 5, all of them are natural numbers. So natural numbers are closed under addition as well as multiplication. Let's get into our next property, commutative property. Here it says A plus B is equals to B plus A. Order doesn't matter for addition and multiplication. For example, 3 plus 5 is 8. 5 plus 3 is also 8. So 3 plus 5 is equals to 5 plus 3. Perfect. Now, let us understand the identity elements. Additive identity is 0. Multiplicative identity is 1. Why 0 is called as an additive identity? When you add any number with 0, you get the same number, right? So it doesn't change. Similarly, when you multiply any number with 1, it still remains the same. It doesn't change. So these numbers don't change anything. That is the reason why we call them as additive identity as 0 and multiplicative identity as 1. Now, what are the inverse elements? Additive inverse. For example, you have a number A and the additive inverse of A is minus A. Because when you add these two, like A and minus A, you get 0. So, minus A is said to be the additive inverse of A. Similarly, vice versa. A is a additive inverse of minus A and minus A is the additive inverse of A. Same goes with multiplicative inverse. 1 by A is the multiplicative inverse of A because when A is multiplied with 1 by A, we get 1. These help us undo the operations. These properties make math predictable and reliable. Let's see where we use these numbers in real life. Natural numbers. We use counting items in the shopping cart, ID numbers, phone numbers, first, second, third place in competitions. Integers. We use for banking, like showing credit as positive and debit as negative. Geography, elevation above the sea level or below the sea level. Time zones, plus 5.5 hours Greenwich Mean Time and minus 700 hours Greenwich Mean Time. Rational numbers. For cooking, we use half cup flour or 1/4 teaspoon salt. Shopping, we say 199 rupees 99 paise, $29.95. Measurements, 2.5 meters or 1.75 liters. And irrational numbers we use for, especially for construction, like calculating the circles with pi. Architecture, using the golden ratio for beautiful designs. Physics, natural algorithms with Euler's number. Every type of number has its purpose in real life. Alright, let's wrap up with the key takeaways. Numbers follow a hierarchy. Natural numbers is a subset of whole, and whole numbers are a subset of integers. Integers are a subset of rational numbers, and rational numbers are a subset of real numbers, and real numbers are a subset of complex numbers. Natural numbers 1, 2, 3 are the simplest used for counting. Integers add negatives, perfect for temperature and bank balances. Rational numbers add fractions, essential for money and measurements. Irrational numbers can't be fractions like pi, root 2 and Euler's number. Real numbers include everything on the number line. Complex numbers add the imaginary part, crucial for engineering and physics. Remember, each number type was invented to solve specific problems, from counting apples to designing rockets. And there you have it, folks. You have just completed the ultimate journey through number systems, from simple counting numbers to mind-bending complex numbers. You now understood how they all fit together. If this video helped you finally understand number systems, smash that like button. Subscribe to Godwills Talent Hub for more awesome math content. Drop a comment below. What math topic should we explore next? And share this video with your friends who need help with math. Remember, keep learning, keep growing. Mathematics is all around us. And now you have the tools to see it everywhere. This is Satish from Godwills Talent Hub, and I'll see you in the next video. Until then, keep calculating and stay curious.